So for a little help on evaluating integrals, that's the purpose of this video. Now I'm going to do a couple problems out of this section 7 through 16. However, if we look back here, we have to remember there is no product rule, no quotient rule for integration, okay? Only the power rule. And all of these, then when I do get a product, right, and I have to remember that this is x to the half, when I have a product, I need to distribute, all right, to get it into the form where I can then use the power rule, okay? I am allowed to distribute here because there's no exponent, all right? Remember, if I had an exponent like to the third power right here, right, then I couldn't distribute, okay, because order of operation says exponents then multiply. But because there's no exponent, I can distribute the x to the 1/2, recalling that this is x to the first, okay? And then if I have a quotient, there is no quotient rule, which means I need to divide each term by the denominator. So coming down here, you are told to identify, it says 7 of the following 10 problems will require use of. So that means there's 3 that are no use of. Okay. So I'd like to try to pick those out first, although I'm not going to pick all of them out for you. Okay, so anytime I can distribute and just multiply and distribute, I don't need use substitution. So like if I look at 14, can I just distribute? Right? Can I distribute the radical x? And the reason I can't is because that's squared. Okay, so I'm going to go to the most obvious and actually probably the easiest integral in this entire section, right? Which is number 16, where I just get x squared plus x. Right, this is definitely the easiest one in this whole section. Okay, I distribute and then I find the antiderivative. Okay, increase the power by 1, divide by the new power, right? Do that on both terms. This is absolutely as easy as it gets. Increase the power by 1, divide by the new power, plus c. Okay, if we can't do this one, we're in trouble. Okay. What else does not require? There's one other one where I can just multiply, where I can distribute. I'm going to leave that for you to identify though. Okay. Now there is another one where I can just divide by the denominator. Okay. If I look at number 13, right, the denominator is x to the half, right? So I need to divide each term by x to the half. And we divide powers of the same base by subtracting the exponents. Okay, so if I rewrite this and I separate to show that I am dividing each term by x to the half in number 13, right, and subtracting the exponents, okay, this is another case where I don't use substitution, okay, because 1 minus 1/2 is x to the half, right, and then I can keep, so I'm going to go integrate dx, do that one separately, right, plus, and then over here I can pull the 5 in front, and 2 minus 1/2, I get 1 1/2, but I don't want to write 1.5 or anything like that. I want to write 3/2. Okay, and then I'm going to let you integrate from there. I think you can do it, right? The increase the power by 1, the divide by the new power. Now, both of these new powers are going to be fractions, which mean you multiply by the new power. So how did that just vanish? Oh, wait, hang on. That's how. Okay, so actually, maybe I will do 1. Okay, so let's extend page. Like, let me do just this part for you. Okay, I'm going to leave this this first half of the integral for u, okay? So over here, I increase the power by 1, which means I add 2 over 2. And my new power becomes x to the 5 halves. Instead of dividing by 5 halves, I multiply by 2/5. Okay, and I had this 5 out in front, right? Because constants can get pulled in front. So I had the 5 out in front, so that conveniently cancels out, or as I'm supposed to say, divides to 1. And this is what you would get for the second half of this problem, okay? So you would complete the entire problem then by doing this part and then finally adding a plus c at the end. Now, let me do one more problem with you then that's a u sub. I feel like 15 looks scary. Right? I could imagine that that just looks intimidating to you. So I'll pick that one as one that we do together. All right, so u, when it comes to selecting u, we always let u be what's under the radical or what's in parentheses, right? So like over here, u is 4x minus 1. Okay, u is whatever is in parentheses being raised to a power, or u is what's under the radical. We know we have to see the derivative of u, give or take a constant, because we can adjust for a constant. Okay, we have to see the derivative of u as part of the integrand, right? And so that's why I can tell, like number 8, I can tell that's going to be a u sub, because when I take the derivative of u, I get 3x squared, right? And there's an x squared. Okay, I have to see the derivative of u is part of the integrand, other than those problems where sometimes we can do a clever substitution and we can still do the problem even though initially it might look like it's not a u sub. All right, so anyway, let me do 15 with you. So erase. Let's erase. All right, so always let u be what's under the radical or in the parentheses. And then we hope to see the derivative of u as part of the integrand, which tells us that u substitution can in fact work for that problem. All right, so for 15, I'm going to let u equal 2 minus 1 over x. Okay, don't put the radical over it. That's what I see sometimes students doing, right? Keeping the radical over it. It's always what's under the radical. Okay, now when I find du dx for this one, all right, derivative of 2, that's just 0. Okay, this, let me come over here. I'll make a little bubble over here. When I go to find the derivative of 1 over x, right, I have to keep in mind that that is x to the negative first. Okay, so derivative means drop the exponent in front, decrease the power by 1, which becomes -2. And then I do my step where I change this back to having a positive exponent, right? So thank goodness I just found that the derivative of u, I've got that, it's positive, right? But I can adjust for a positive or a negative, and I can also adjust for a constant. Okay, so derivative of 2, that's 0. Derivative of -1 over x is actually -1 over x squared. Okay, so that's kind of convenient that the negatives, I have a negative and then a negative, so that becomes a positive. Okay, so if I solve for dx, right, let me think in terms of cross multiplying this. Okay, if I cross multiply this, I get dx equals x squared du. Okay, then I know that if I want to be a good mathematician, I just have to be a good substituter. Are you tired of hearing me saying that yet? Right? Once you get to the point where you're sick of hearing me say that, then I know I've done my job and taught you how to be a good mathematician. Okay, so we come up to what the original problem in number 15, and everything gets replaced with its equal. Okay, so I have 1 over x squared still. I have u, right, radical u, so I'm going to write that as u to the half. And then dx gets replaced with x squared dx. Okay, conveniently, these divide to 1, so these are gone. Okay, if I couldn't get rid of the x squareds, I'd either, number 1, have to conclude I don't have a u sub problem, or number 2, try to do one of those clever substitutions where I take my statement of what u equals and I try to manipulate it and solve for x. Okay, but conveniently those canceled. And as I've said many times, if you don't get a nice, easy antiderivative, right, or integral, right, and it's not easy to find the antiderivative, then something is wrong. Okay, so I increase the power by 1, right, so I get u to the 3/2 divide by the new power, which is multiply by the reciprocal, so that I don't get complex fractions, plus c. Okay, and then my final answer, which I would write over here if I had room, right? Doesn't kind of make sense to go right to left, but this is where I have room, so this is where I'm going to write it. My final answer then, plug back in for u, right? And this scary looking problem ends up really not having been so bad. So it's this to the 3/2 plus c. Okay, next video, I will go into some of the, quote, clever substitutions, as I call them.